Hello everyone. In this session, I will share with you a new topic that is on the discrete Fourier transform. First of all, why do we need to learn the discrete Fourier transform? This is to examine the sample signal in the frequency domain. Fourier transform is used to decompose the time series signal into a frequency component. And Fourier transformation is implemented in many DSP systems, either in time domain or also in the frequency domain. So Fourier transformation also implemented to speed up the algorithm. So in this topic, you will learn how to obtain the discrete Fourier transform. Discrete Fourier transform can be obtained by, first of all, using formula, the second, properties, and the third one is the FFT, that is the fast Fourier transform, either in the decimation in frequency or decimation in time. So first of all is using the formula. This is the formula for the discrete Fourier transform. Okay, x DFT. DFT is discrete Fourier transform. X DFT k equal to the summation from n equal to 0 to n minus 1 xn. Xn is the discrete signal. Okay, exponent minus j 2 pi nk over n. So the k can be from 0 to n minus 1. Whereas for the inverse discrete Fourier transform, IDFT, can be obtained by xn equal to 1 over n and then summation from k equal to 0 to n minus 1 x dft k exponent positive j 2 pi nk over n. So take note that the difference of the discrete Fourier transform and the inverse is the exponent here. This one for the discrete Fourier transform, you have the negative. The exponent is a negative. For the inverse, the exponent is the positive and also is divided by n. So the exponential of this positive or this negative or the positive is referred to the relation in periodic in both n and k with period of n. Okay. Now, let's look at the example 4.1. Given the xn is equal to 1, 2, 1, 0, find the discrete Fourier transform of the xn. In order to solve this question, we need to follow the formula, the x dft k equal to the summation xn exponent. Okay, so the k must start with 0. Also for the n also start from 0. Okay, now we start with k equal to 0. So means that the x dft k means that dft 0, the first dft 0, that is equal to the summation, the n equal to 0 to n. N, so you count. You count here 1, 2, 3, 4. So n minus 1, so 4 minus 1 is 3. So up to 3 only. Then xn exponent 0. So this means that it's a summation from n equal to 0 to n equal to 3. So xn. So xn, you look at here is 1, 2, 1, 0. So you sum up 1, 2, 1, 0. So you get 4. So this is the x dft 0. Then next is when k equal to 1. So I have the x dft k, that is x dft 1 equal to the summation. Again is n equal to 0 to 3 xn. Now I have the exponent minus j 2 pi n k is 1, so I just write it as 1 divided by 4 because the n is 4. So this is from xn exponent minus j pi n over 2. So I can solve it. Okay, xn when n equal to 0. When n equal to 0, I have the value of 1. Okay, I have the value of 1. So I have the 1, then exponent minus j pi n equal to 0. Okay, divide by 2. Okay, then plus with the second xn, that is the 2. Okay, so 2 exponent minus j pi when n equal to 1 divided by 2. Okay, then plus with the third xn. Okay, third xn, that is 1. And the last one is 0. Okay, so the third one is 1 minus j pi n equal to 2 divided by 2. Okay, plus with 0. So we simplify 1, and then this one is exponent 0. Okay, so 1 plus this is 2 exponent minus j pi over 2, and then plus with this one is exponent minus j pi. So now we have the 1 plus, okay, exponent minus j pi over 2. What is the answer? Okay, what is the answer? How do you get the answer? Actually, you can get the answer, you convert it using the Euler formula. Do you know what is Euler formula? Euler formula refers to exponent plus minus j theta equal to cos theta plus minus j theta. Okay, so you can, this part you can convert. Okay, you can convert. So for example, exponent minus j pi over 2, you can change it to cos pi over 2 minus j sine pi over 2. Then you press the calculator. Okay, you press the calculator. I have pressed the calculator. I obtain this one is minus j. So make sure when you press the calculator, it is in the radian form. Okay, it's in the radian form because you're using the pi. So this one from here, I get minus 2j. And then this one also the same method that I teach you just now. So you get plus minus 1. So I get 1 minus 2j minus 1, I get minus 2j. So 1 minus 1 is 0, so minus 2j. Okay, that is the when k equal to 1. Now we check for when k equal to 2. So when k equal to 2, x dftk, so ft2 equal to, again is from n equals 0 to 3, xn exponent minus j2 pi n over 2 pi n2, okay, over 4. So this is equivalent to exponent minus j pi n. So this one cancel with cancel. Okay. So you have 1. Okay, x0 is 1. Then you have the exponent minus j0. Okay. And then plus with exponent minus j pi. Plus with 1 minus exponent minus j 2 pi. Alright, so when I simplify, I get this one is 1, so I get 1 plus 2 exponent minus j pi plus exponent minus j 2 pi. So this one is 1 plus, so when you press the calculator, then using the method that I teach you just now, so exponent minus j2 pi times 2, you get 2 minus 1 plus with cos 2 pi. Oops, this one I can straight away write it down 1, okay, because I already simplified. So I can get 1 minus 2 plus 1, so I get 0. Next one is when k equal to 3. So x dft3 equal to the summation from n equal to 0 to 3 xn exponent minus j 2 pi n and k is 3 divided by 4. Okay, then n equal to 0 to 3. After I simplify, I still get negative pi 3 pi n over 2. So I can have the x0 is 1, then exponent minus, this is exponent 0. Okay, and then plus 2 exponent minus j 3 pi 1 over 2 plus 1 exponent minus j 3 pi 2 over 2, and then plus with 0. So this one is equal to 1 plus 2 exponent. So this one is when you press the calculator for the 2 exponent minus j 3 pi over 2, you get 2j. This one is the exponent minus j 3 pi. Okay, so when you solve it, you get minus 1. So equivalent to 2j. Okay. So at the end, you will get the DFT is x DFT k equal to, okay, you copy down everything. First one is 4. Okay, first one is 4. Second is negative 2j. And the third one is 0. And the fourth one is 2j. Okay, then we copy down the answer. Don't forget your origin. Okay, so that's all how to find the XDFT using the formula. Next is the property of the discrete Fourier transform. We have the time shifting property and the frequency shifting property, modulation, folding, product, convolution, correlation, central ordinates, and possible theorems. So we will look at it one by one. In discrete Fourier transform, we also have the property of symmetry. The symmetry property is quite easy. That is the conjugate symmetry at about the origin. So x dft minus k is equal to conjugate of the x dft k. So since DFT is a periodic, x dft minus k is equal to x dft n minus k. This is also means that the conjugate symmetric about the index k equal to 0.5 n. So the x dft minus k is equal to the conjugate of the x dft k, also equal to x dft n minus k. So let's say if n is the odd number, the conjugate symmetry is about half of the integer value, 0.5 n. This graph will clearly tell you the symmetry properties, and we call it the n equal to 0.5 n, which is we name it as a folding index. If when n is an odd number, n equal to 7, odd number. So let's say this is 0, 1, 2, 3, 4, 5, 6. Okay, so it's n equal to 7, so it's an odd number. So 0.5 times with the 7, you get 3.5. So 1, 2, 3.5. So this is n over 2. So the value will be, so this value will be the conjugate, this value, okay, this value will be a conjugate of this value. So this value will be also the conjugate of another value. So this is as a symmetric, the property of symmetry. So let's say n is even, also the same. Let's say you have n equal to 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 times with 0.5, so you get 4. So 0, 1, 2, 3, 4. So you get in here 4, x4. So the value of this one and this one is a conjugate. Okay, xk equal to x conjugate of n minus k. So the value are the same, just that is a different in terms of the sign of imaginary part. The magnitude will be the same, only the difference is the sign in imaginary part. Okay, for example, given the n equal to 7, k is from 0 to 6. Okay, if xdft 3 equal to 1 plus j, what is the xdft at 4? So when n equal to 7, k is equal to 0.5n. This is 3.5. Okay? So this means that all the value above the 3.5 will be repeated symmetrically. So this means that when I draw is 0, 1, 2, 3, 4, 5, 6. Okay? So this is the 3.5. So this is the folding index. So this value will be the same, just for the amplitude and imaginary, the sign at the imaginary will be changed only. Okay, so just now, if let's say I have the x3 is 1 plus j. Okay, what is the x4? So since the x3 and 4 is symmetrical, okay, so x4 is the conjugate of the 7 minus 4. So I will get the x dft conjugate 3. So conjugate 3, that is 1 plus j. x3 is 1 plus j. So conjugate, I get 1 minus j. So that is quite simple and straightforward. And you don't need to calculate using the formula. Alright? So we can understand. Next is about the central ordinates. Okay, the computation of the DFT is easy to compute at k equal to 0 and at k equal to n over 2 using the central ordinates theorems. So x dft 0 is the summation from n equal to, for n equals 0 to n minus 1 xn, whereas for n over 2 is using the formula summation of minus 1 power of n xn. So this is the x formulas for x dft, and another, the below one, is the formula for the xn, how to get the xn back. And also bear in mind that for the n over 2, this n should be for the even n only, not for the odd n. Now let's look at the example. If the xn given is the a, 2, 3, 4, 5, 6, b, if x dft 0 is 20 and x dft 4 is 0, find the a and b. In order to solve this, you must still remember the formula for the x dft. So x dft k equal to summation of n equal to 0 to n minus 1 xn exponent minus j 2 pi nk over n. Okay, so this is the formula. So as given in the question, x dft 0 equal to 20. So you have x dft 0 equal to the summation n equal to 0 to 7 xn exponent minus j 2 pi n. So the k is 0, equal divided by n. So this will equivalent to summation n equal 0 to 7 xn only. So in the question given, x DFT is 20, so it's 20 equal to a plus b. Sorry, a plus, follow the question xn, so a plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 and plus b. So when I solve it, I get a plus b plus all this is 27. So a plus b equal to negative 7 when you bring the 27 to the left. So it's negative 7. So I assume this is the equation number 1. And then the question given also x DFT 4 is equal to 0. So we also can use this x DFT 4 equal to the n equal 0 to 7. Okay, if we look at here, we can use the central ordinates. Okay, we can use the central ordinates. That is summation from 0 to n minus 1 minus 1 power of n xn. So this is the central ordinates. Okay, the first one is a negative 1 power of 0. The first value is a, and then the second value, when n equal to 1, x1 is the value of 2. Okay, we follow the value of 2, 3, 4. This is the xn value. And then plus with negative 1 power of 2, and then 3, plus negative 1 power of 3, 4, plus with negative 1 power of 4, the value is 5, and negative 1 power of 5, the value is 6, plus negative 1 power of 6, the value is 7, plus negative 1 power of 7, the value is b, the last one. So we can simplify, we get a, and then we add up this all thing, we get plus 3. So okay, we solve everything, we get plus 3. Okay, minus b. So a minus b equal to minus 3. So this is equation number 2. So now I have equation 1 and equation 2, so I can use as a quadratic equation. So 1 plus 2, I get 2a equal to negative 10. Okay, a plus b and a minus b. So plus and plus, I get 2a. 2a equal to minus 10. So a equal to minus 5. So this is equation number 3, and I substitute 3 into 1. So I have a plus b equal to minus 7, minus 5 plus b equal to minus 7, b equal to negative 2. Okay, so I have solved the question in which the a is equal to minus 5 and b equal to minus 2. Okay, that's all for the question. Next one is the circular shifting. It's also a type of the shifting, but just that is a circular shifting. So the circular shifting requires the signal value from 0 to n minus 1. So in order to find the discrete Fourier transform of the time shifted signal, the value must also be selected over from 0 to n minus 1 from its periodic extension, since the DFT is for the periodic signal. So next, how to implement the circular shifting. Okay, to generate a xn minus n naught, move the last n naught sample of xn to the beginning. And then to generate the xn plus n naught, move the first n naught sample of xn to the n. So this is how the circular shifting works. Whereas for the circular folding, it generates the signal for x minus n from xn. And it creates the periodic extension of the folded signal and pick the n sample of the periodic extension over 0 to n minus 1. Now let's look at the example on the circular shifting. Given the yn equal to 1, 2, 3, 4, 5, 0, 0, 6 and find the one period of the circularly shifted signal, fn equal to yn minus 2. So as you know, the yn is 1, 2, 3, 4, 5, 0, 0, 6. Okay. So the signal actually is repeated. Okay, 1, 2, 3, 4, 5, 0, 0, 6. So the signal is repeated. Okay, let's say if the yn is 1, 2, 3, 4, 5, 0, 0, 6, and then if fn is yn minus 2. Okay, n minus 2, where is the origin? Origin is at, let's say, just now origin is here, right? And then n minus 2 means that you shift the origin 2 units to the left. Okay, 2 units to the left. So for periodic, we always start at the origin n equal to 0. So your answer is 0, 6, 1, 2, 3, 4, 5, 0. Okay. It still remains as a how many number? We can count 1, 2, 3, 4, 5, 6, 7, 8. So we still remain 1, 2, 3, 4, 5, 6, 7, 8. Okay, so from here to here, it still remains as a n equal to n. For the next question, Gn equal to yn plus 2. This is also the same, the signal just now repeated. Okay, just now the originary is from 0, is from, the question just now is 1. Okay, the origin is at 1. Okay, and then you move 2 units to the originary, the origin is here, so you move 2 steps to the right. So it starts from 3. So now means that I still have the value. Signal is repeated, so 1, 2, 3. So starting from here, my new origin, this is my new origin, I have the 8 sample. 1, 2, 3, 4, 5, 6, 7, 8. So my answer is starting from here to here. So the answer is 3, 4, 5, 0, 0, 6, 1, 2. And then the third question is Hn equal to y minus n. Okay, minus n means that it's a flipped folded signal. So the folded signal, this means that I have the 6, 0, 0, 5, 4, 3, 2, 1. Okay, and then 6, 0, 0, 5, 4, 3, 2, 1 is a folded signal. Okay, and then this is my origin initially. So I have to count 8 sample. So 1, 2, 3, 4, 5, 6, 7, 8. So this is my answer. 1, 6, 0, 0, 5, 4, 3, 2. Okay, so must remember for periodic, always start with the origin at n equals 0. And then the next one is the circular symmetric. For a real periodic signal with the period n, circular even symmetry is xn equal to x, capital N minus small n. Whereas for the odd symmetry, there is the minus x, capital N minus n. So from here we know that this is n equals 0, 1, 2, 3, and 4. Okay, so n, we have total of n equal to 5. Okay, 1, 2, 3, 4, 5. That is from 0 to 4. We have n equal to 5. So by using the circular symmetry, and even symmetry, okay, A is equal to x2. So this is the even. Okay, so x2, we use the even symmetry. So even is xn equal to xn minus n, right? Okay, so this is the even symmetric. So we use this formula. So xn is capital N is 5 minus the small n is 2. So we have x3. And x3 in this question, that is equal to 0. So A is equal to 0. Whereas for x4, we have the also is an even, so x5 minus 4, that is equal to x1. So x1 in this question is 2. So B is equal to 2. Okay, this is also similar to the folding index. Okay, it's just like just now. We have the 0, 1, 2, 3, and 4. Okay, the value is 6. And then 2. And then we have the A. And then x3 is 0. And then we have the x4 is B. Okay. So the folding index is, the n is 5. So 0.5 times 5, so you get 2.5. So this is the folding index. So easily we can obtain that the x2, x3 is the same. So we get the same value. And x1 and x4 also the same. So this is similar to the folding index. So that's all for the first part of the discrete Fourier transform by formula and some properties. Okay, hope you can understand and enjoy your watching. Thank you.